Okay, so now continuing to read through this foundational paper on generalized linear models, we are now at this statement right here that then 1 implies that the mean of z, the random variable z, equals the first derivative of the function g with respect to theta. Okay, so remember we've already shown equation 1 in a previous video. We showed equation 2 in the previous video, and then we discussed this statement right here in a previous video. And I'll include the link to this playlist in the description of this video, okay, if you need to back and catch up on some of those. All right, so let's go to the whiteboard or blackboard here and talk about this. So we've already shown this, and we've also already discussed this right here. Okay, so we're going to need both these to say then 1 implies, the equation 1 is going to imply this relationship right here. So mu equals the expected value of z. That is just a definition. Really what we're talking about is why is it that the expected value of z equals this first derivative of the function g. Okay, so let's start with what equation 1 says. It says that the expected value of the first or of the partial derivative of the log likelihood with respect to theta equals 0. Okay, and then we showed in the previous video this piece right here equals what I see right here, the alpha of phi times z minus the first derivative of g with respect to theta. So let's go ahead and write that in. Okay, so I have the expected value of alpha of phi, okay, so that's the function of phi, times z minus g of theta, okay, and then close parentheses on the expected value. Okay, let me change that back to yellow. Equals 0. All right, so now let me go ahead and just do some manipulation here. Let's just go ahead and distribute this alpha of phi. Okay, so I get alpha of phi times z minus alpha of phi times g prime of theta. Okay, so this equals 0. So now let's use our properties of expected value. I have an expected value of a difference, which means I can take the expected value of each piece. Okay, so I get the expected value of this piece minus the expected value of that back piece. Okay, I'm still going to get that equal to 0. So the expected value of alpha of phi times z and the expected value of alpha of phi times g of theta. Okay, all right, now once I'm here, remember our random variable is z. So alpha of phi is just a constant, so it can be pulled out of the expected value. All right. And, oops, I forgot to close that parenthesis right here. Alpha of phi times g prime of theta, this is just a constant. It doesn't include z at all. So the expected value of a constant is just itself. Okay. All right, so now let's just do some algebra and rearrange and solve for the expected value of z. Okay, so first thing, let's go ahead and add to both sides this alpha of phi times g of theta. All right, and then divide both sides by alpha of phi. Okay, and these cancel, and you can start to see it now. The expected value of z equals g of theta, g prime of theta. Okay, and that's what we wanted to show. So we can see now, okay, so basically I put together this information about equation 1 with this statement here, and I can see it's relatively simple to show that, okay, the expected value of z, which we define as mu, equals the first derivative of the function g with respect to theta. Okay, and that's what we've shown here.